So today we'll be discussing why we need laminate when we are constructing a leaf spring, why we are not able to use a single solid piece, and why we are going to have laminates like this. So let us first consider a single solid piece, a beam which is subjected to bending moment M. The dimensions, this may be I into H and this may be B. If this particular beam is subjected to this moment, then it will be deformed like this. So the deformed shape is like this. It will have a common radius of curvature, and the upper fiber will be in tension and lower fiber will be in compression. The cross section of the beam can be represented like this, and the stress distribution like this. So here it is B, that is the width of the beam, and this depth is I into H. So the bending stress given for this beam is, at any section, it is M by Z. And if we talk about maximum stress, then it is M maximum divided by Z. And M maximum is to be obtained by bending moment diagram, but for given case it is constant, so we will write down M by Z. So sigma maximum is M by Z, where Z is 1 by 6 B H square. So H here is I into H, so we will write down I into H square. So we can have it is as sigma maximum is equal to 6M divided by B I into H whole square. So now let us see what is the difference. What is the difference when we have different laminates instead of a single solid piece? So now let us take another example. If we take laminates and they are placed over one another so that they can slide over one other, it is assumed that all laminates take same radius of curvature and enjoy their own independent neutral axis. The force distributed on all the laminates and the stress in each laminate is independent of each other. The stress developed in each laminate is computed by bending moment due to the force shared by that particular laminate. If we see that this was our laminates number of, there are 4 number of laminates. When a bending moment is applied, they will take, this is the deformed shape of the laminate. Each laminate is bent separately because they can slide over one another. So that is why they will have their own neutral axis, and the stress distribution is in each laminate is like this. So I have enlarged the diagram to show what is the effect. This is the cross section. This first number laminate, second number laminate, third number laminate, fourth number laminate. The neutral axis of first laminate will be like this, because this fiber of the first laminate will be under tension and this fiber of first laminate will be under compression, and fiber at this interface of second laminate will be under tension and the lower fiber of the second laminate will be under compression because they are deformed separately. So this is the enlarged stress distribution. This is stress distribution for laminate number 1. This is stress distribution for laminate number 2. This is stress distribution for laminate number 3. This is stress distribution for laminate number 4. So we can write down that bending moment that was applied on the beam will be shared by all the laminate. If there are 4 number of laminate or if there are I number of laminate, we can write down this is equal to Mi, where M1, that is resistance, is given by sigma 1 induced in laminate number 1 multiplied by its section modulus. M2 is sigma 2 Z2 and so on. So we can write down M is equal to sigma Z1 plus Z2 and Zi. But in this particular case, Z1, Z2, Z3, they are same. Z1 is equal to Z2 is equal to Zi. So I can write down this equation as M is equal to I sigma into Z. So sigma, that is stress in this laminate, is equal to 6m divided by I BH square. Here there is another important point. We have substituted sigma instead of sigma 1, sigma 2. I assume that sigma is constant. This is because we know that sigma is equal to E by R into Y. So here we know that E is constant and R is also constant for each laminate. So that is why sigma 1 will be equal to sigma 2 will be equal to sigma 3 and so on. So that is why we have substituted sigma for sigma 1, sigma 2 and taken this as common. So now we can see very important aspect here. The stress in each laminate is equal to the stress in member of width I into B instead of I members of width H. So here this point is very important. Let me again explain. This is equal to, this is the equivalent width of the member. So we can assume that this stress is the value of stress let me again explain. The stress here in each laminate is equal to the stress in a member of width I into B instead of I members of width H. The equivalent section is obtained by placing all laminates side by side. It means if I place these laminates like this or like this, this is first laminate, this is second laminate, this is third laminate, and here it is fourth laminate. So and if I apply bending moment M like this, so this is nothing but I into B and here it is, the thickness is H. So whether we calculate stress here in a member which is having I into B width and H thickness, or we calculate stress in a member where these are placed like this, the width is B and there are I members of H thickness, the stress will remain same. So this concept will also be used in a laminated spring further, and we can see the difference between the stresses. The stress we have obtained in when we have used only single solid piece, and stress when we have this value in single solid piece. This was sigma was equal to 6m over BIH square. So stress here it is less. So sigma single and sigma laminated. So sigma single is less as compared to sigma laminated. So this means we lost strength in laminated spring, but this loss in strength is, you can say, accepted as it reduces the stiffness of the assembly. Another example, we will take a numerical problem, a numerical example, so that it is explained how much stiffness is gained when we lose some strength by laminating the spring.